We have an exam a week from today that is going to cover everything up through MongoDB, which we will be starting to discuss today and we'll finish up talking about on Tuesday. And if you're looking for some sample exams, we have a sample midterm from a couple years ago. It obviously doesn't have anything from NoSQL on it. I shouldn't say obviously. You don't realize this is the first time I've taught NoSQL, so there will not be any example questions from NoSQL. However, the NoSQL questions and the MongoDB questions will be multiple choice and multiple answer. They will not be forcing you to work them out. So as you can see, toward the end of it, I have you typically work things out here. You had to write some SQL queries. You had to actually the grad students had to write relational calculus queries. While this test did not have relational algebra queries on it, I expect you to be able to write a relational algebra query as well. There'll definitely be something with either extendable hashing or B+ trees in terms of having to do some kind of insert or delete. We don't worry about deletes for extendable hashing. We never talked about it. So for B+ trees, you need to be able to insert and delete. For extendable hashing, you just need to be able to insert and need to be able to draw ER diagrams. And you need to be able to, given a description of the problem, you need to be able to draw the ER diagram. Given a description of the problem, you need to be able to give me functional dependencies and move from first to second normal form and second to third normal form. Okay, so usually, and in this case will also be the case, I usually have at the end of the test a description of one or two databases that you're using for the rest of the test. So normally you'll first go down, read through it because that is required in order to answer often some of the multiple choice and multiple answer queries. I've almost finished the exam review guide. I hope to finish it later today after lecture and get it posted. It will be posted here with the exam, so there'll be a up here, exams from this semester, there'll be a review guide for you to look at. You'll have the whole class period. There'll be, it's closed note, closed book. And any questions about that? Yes?
Would we be like writing it directly on like the answer sheet? We bring it or
Nope, you'll be writing directly on the answer sheet. So no need, all you need to bring is a pen or a pencil to this exam. Okay. Other questions? Okay. So also, since this is the first time I have taught NoSQL and MongoDB, I don't have quizzes for them yet. I always develop the quizzes after I've taught the material the first time because it's always a little uncertain how to write the quiz until I've actually gone over the material once. So there's no quizzes either after this lecture or the one on Tuesday, but there is an after-class activity today. It's very quick with JSON. I think it's chapter, I forget which. Just make sure you do the after-class activity. It involves writing out a JSON object, so not very difficult. Okay. So after, well, we'll worry about after everything once we get to a week, what is it, 2 weeks from today? Yeah, 2 weeks from today we'll start with the scripting language is part of the course, and there will be some things changing. You'll have different sets of after-class activities, not so many quizzes anymore, more after-class activities from the textbook. You're going to be back to doing before-class activities in the textbook. Your homework assignments are going to be much more infrequent after the exam because essentially you're going to be working on a project rather than homework assignments. The homework assignments are more to force you to do part of the project before the last week of class. So the pace of the homework assignments slows down. probably most of you will find the class gets easier, which is for many of you good, because normally it's the opposite. Normally in the second part of the semester the class gets harder, not easier. So at any rate, perhaps some light at the end of the tunnel for those of you who've struggled a bit with some of the concepts in the database portion. Okay, so with that covered, we're going to move on to talking about away from relational databases, and we're going to be talking about the new kid on the block, which is NoSQL. And I don't have the right, how can I not have the right set of notes? Just a second. There we go. Okay. Okay. Let's start this. Okay. So basically, relational databases are good for doing structured data. So if you're doing inventory, if you're Amazon and you're keeping track of your inventory of books or inventory of products, or you're a bank, you're trying to keep track of the transactions, deposits, withdrawals. If you're eBay and you're keeping track of items for sale, you have a lot of structured data. You probably want to use a relational database. When social media sites started developing, they found that their data wasn't quite so suitable for relational databases. They had what was called semi-structured data, meaning that not with relational databases, you tend to have a fixed set of columns for each relation. With social media, what they were finding was that entities could have many sets of attributes, and not every, what they called a document, could have the same set of attributes. So if you, for example, had, well, let's just think of an address, okay? A street address typically has a number, the street, and a suffix such as lane, drive, road. So for example, 4300 Nayland Drive. But if it's an apartment, it may have an apartment name and an apartment number. If it is a post box, it may have P.O. box without any other information. So that's an example where you have the same thing, an address, but three very different ways of representing the address. Okay? And if you try to put all the attributes for an address into one table, it's not really good, because you have to have pretty much all the attributes for a street address, all the attributes for a P.O. box, all the attributes for an apartment, and two of the three sets of attributes will be null for every entity. So this isn't good. Social media has the same thing. When you have things like, say, a blog post, you may have comments associated with it, or you may have no comments associated with it. Maybe you have likes and dislikes, maybe you don't. Maybe there are tags or keywords associated with it. Maybe they're not. Not only that, but social media documents have a lot of what are called composite attributes or multi-valued attributes, things that relational databases have to put off into separate tables. Multi-valued attributes have to go off in separate tables. So for example, a blog post may have multiple comments. That's kind of like a multi-valued attribute. Might have multiple keywords or tags. That's a multi-valued attribute. So social media posts tend to have a lot of features that are not well supported by relational databases. So you can say, let's make this full page for a moment and get rid of this. So social media documents. Things that are different, you might have lots of different attributes. I'm going to abbreviate attributes this way. Lots of different attributes, only some of which are in each document. And social media often talks about, it actually does have this notion of a document rather than an entity. A Twitter post would be a document. A text message would be a document. A Facebook post would be a document. They talk in terms of documents. Okay, so you might have lots of, which means lots of sparse data. Lots of nulls. Okay, lots of different object types. Okay, so the way that's handled in the relational databases with supertype, subtype. But every subtype ends up in a different relation, whereas you might want the different documents to all be in the same collection. So lots of different types of entities, and I'll say subtypes, supertypes. Okay, lots of multi-valued attributes. Okay, say like comments or keywords or tags, I'll say. Okay, often lots of composite attributes, which can be handled by a relational database, but they end up separated. Okay, rather than like an address, the attributes have to be, they can't be, you can't say address and then have sub-attributes for the address. Instead, you just have street, zip code, city, state, but it's not all grouped together under one attribute heading or in one object. Okay, so lots of composite attributes, lots of multi, okay, and I'm going to say lots of weak entities. Okay, so weak entities are entities that are only present if the strong entity is present. So like tasks for a project. Project is the strong entity, tasks are the sub-entities. So oftentimes you'd like to be able to store the weak entities with the strong entity. You'd like to store all the subtasks with a project. If you have a bunch of comments and you decide that those are entities, you'd like to store all the comments with the blog post. If you have a bunch of exams, you might want to store all of those exams with a student. So you can't do that in relational database. In relational databases, you have to join. So in relational databases, whoops. You use joins to get info on weak entities. So there's a bunch of things about social media data that is not well handled by relational databases. And This caused the developers of social media to cast about for some kind of alternative type of database that might address these difficulties. Okay, so one difficulty is that the storage for relational databases could blow up as you have all of this sparse data. Okay, the other problem is all these separate tables require joins, and joins are an expensive operation. So what they were finding was they were joining lots of different tables, and oftentimes they felt relational databases couldn't keep up with the number of queries that were being asked of them. Okay, so their performance was too sluggish. Okay, let's see, what other issues do we have with relational databases? Structured data. Okay, the third thing is to increase the performance, what they wanted. So let's just say, what are the down or disadvantages then of relational? Before I do that, okay, I will say relational DBMSs for social media. It's not just social media, but this was the driving force. Okay, so sparseness, okay, can lead to large storage. Okay, tables, many tables lead to many joins, which can be slow. Okay, and then there's a third characteristic, and before I get to that, I have to get to something that all relational databases maintain. It's called ACID. These are 4 properties maintained by relational databases. A stands for atomicity. C stands for consistency. I stands for isolation. And D stands for durability. So these 4 characteristics are maintained by all relational databases. It's very important for what is called transaction handling. So ACID comes into play for transaction management. So many transactions consist of multiple operations. So each transaction may have multiple operations or queries. And what you want to do is you want to make sure that you can execute transactions in parallel. Also, that if a transaction crashes in the middle of its operations, that the database is not left in an inconsistent state. Okay, so the atomicity says that a transaction either completes or its operations are rolled back if it fails. So either the operations all succeed or you roll them back. It's binary. You can't have some of the transactions succeed and some fail. That's atomicity. They rise and fall together. Consistency means that you take a transaction, brings a database from one consistent state to another. So transaction brings the DB from one consistent state to another. Okay, which means all constraints are satisfied and redundant data is consistent, or is not contradictory, so it's consistent. It's not, is identical is probably the best way to put it. Redundant data is identical. So all redundant data, like if you have foreign keys that, if you update a primary key, all foreign keys that point to it are updated as well. If for some reason you have a duplicated attribute, then the values of that attribute are, all values of that attribute are made consistent. But mostly it has to do with if you update a key, all foreign keys are also updated. Or if you introduce a new foreign key, that foreign key points to a valid primary key. Otherwise, it's null. Okay? Isolation means that it doesn't, transactions do not interfere with one another. So parallel transactions do not interfere. Not interfere or create race conditions, i.e. do not create race conditions. Okay, and that means locking. So that requires locking in order to enforce isolation. So you have to lock relations while an operation is done on it, or maybe lock if you have a customer in a bank account and you're processing deposits and withdrawals on that customer. You have to lock that customer when, say, a deposit is being made because, I'll get you, Emily. So you don't want to have, say, a balance of $80, and let's say that the deposit is made and it changes its deposit for 120 and there's a check for, let's say, minus 70. What you want at the end is that the amount in the account is now $130. What you do not want is that, let's say, the deposit sees 80 and changes it to 200, and the withdrawal sees 80 and changes it to 10, and you end up with one of these two figures instead of 130. That would be a race condition. So you need some kind of locking to ensure that you don't get race conditions. Okay, how would the bank feel about not having isolation? In my notes I said probably bankrupt is how it would feel. Okay, so it's absolutely critical that it have isolation. Yes, Emily? Yes, you'd be using some kind of mutex probably. Okay, and let's see, is that going to give me an eraser? Probably not. Is that going to give me an eraser? I would love to have an eraser. Nope. Oh, I'd love to have an eraser. And it is saying denied. How come it won't give me an eraser? Okay, well, wall this off. Durability. Durability means that once a transaction commits, it cannot be forgotten. Even if the database crashes. So that's durability. Once a transaction commits, its effects are there permanently. It can't be forgotten. So these 4 properties are super important for relational databases, and especially for financial transactions, they are critical. For inventory management, they are critical. You don't want, if you have one inventory item left, you don't want to have a race condition with 2 people grabbing the same inventory. So these 4 conditions absolutely critical for many types of applications, but not for social media. Okay, so for example, if you have 2 different comments come in, it may not be necessary for someone looking at a blog post to see those newest comments. Okay, it's just not going to break the bank, so to speak, if you are unable to get the latest comments to someone when they look at a blog post. Or if the tags are updated, it's not the worst thing in the world if someone looking at the blog post doesn't see all of the tags. So social media would be happy to have these constraints enforced, but they impose a performance penalty, especially locking and consistency. Impose performance penalties. Locking in particular makes it hard to distribute a database across multiple clusters. So social media, to make things faster, often likes to distribute things across multiple servers. And that increases the ability to respond to multiple requests. For example, they actually may duplicate data on multiple servers. Okay, so you might have one server in Los Angeles and one server in Boston. They both have the same social media post. So someone in New York would get the Boston server and someone in San Diego would get the LA server. And they'd get a faster response. But the problem is the blog post is duplicated in 2 different places. And if someone changes the tags on the Boston server, someone may not see the tags on the LA server for a minute or so, say. That's a consistency issue. Okay? It's not in a consistent state at that point. The values for the tags at the Boston site are not the same as the tags at the LA site. Okay? Locking becomes an issue on clusters. If you have to lock on 2 different machines, it's a lot more complicated and it slows things down. In practice, there's not a locking, you don't really have distributed relational databases across different machines because the locking is just too complicated. It can be done, but the performance takes a big hit. Okay, so consistency and isolation are 2 performance killers that social media is willing to relax. Okay, so the third thing that I can now say is that it is difficult, okay, because of ACID. Whoops. I don't want that. Sure as heck don't want that. And somehow I got off the right just a moment. Crash, nice. Okay, well, for a moment, I'm just going to show you, well, no, I need to go back into. Yeah, let's see, do I want to try to recover? This is probably a mistake. Ooh, look at that. It did recover. Kind of. Maybe. Good. Hey, look at that. It did recover. All right. Okay. So the third problem is that it's hard to distribute a relational database across multiple servers because of ACID restrictions on transactions. Okay? So, again, social media is not really as concerned about isolation and consistency as many applications like financial transactions or inventory management. So they're willing to relax them. Okay, so NoSQL is going to do a number of things. First of all, okay, so how NoSQL approach or addresses these issues. Okay, the first thing is they hit on JSON or XML, but usually they use JSON as new descriptive languages. As you saw today, JSON is key value pairs. Uses key value pairs to store data. So now you don't have to store attributes with null values. Okay? So don't have to store attributes with null values because all attributes are now named. So that's their answer to sparseness, is you name all your attributes. Now, that works really badly in dense when the data is dense. Okay, relational databases name their columns with schemas. So relational databases have a schema. It says, okay, a bank account has a bank ID, it has a balance, it has a name. For the time being, we'll just say that. Okay? So you don't, when you store things into a relational database, you just store the values. You don't store the attribute names. But if you had to store a similar document in a NoSQL, you would have to say something like account number, and you'd have to actually write it out and store it, account number and whatever it was. And then you would have like customer name, and again you'd have to write it out. And you'd have a balance. And again you'd have to write out the name balance. So the problem is you're taking up a lot more storage by naming the attributes in every object. Okay, so it's a trade-off. They're hoping the sparseness makes up for the fact that you're having to name all the attributes. Okay? They are able to, so NoSQL allows lists, or JSON sometimes calls them arrays, to represent multi-valued attributes. Okay, it uses, you may remember from reading today about JSON that it has objects. So it uses objects to represent composite attributes. So it can group objects to represent or group composite attributes like, say, address or date or name. Okay, it also uses objects. You can store lists of objects. Which means you can store lists of weak entities associated with you. So for example, if I had a student, I could store lists of exams. Those exams themselves are going to have attributes like maybe the score, comments, the TA or the grader, maybe the problems that were gotten right or the problems that were gotten wrong. So JSON provides a way an alternative way to represent your documents. So NoSQL does talk about, so in a relational DB, you would talk about a tuple or a row. In NoSQL, you would typically call it a document. And in a relational database, you would talk about a relation. In NoSQL, you call it a collection. So NoSQL is often talking about collections of documents. Okay? Social media things are often referred to as documents. And you organize these documents into collections. Okay? And as I said, each document is represented as a JSON object. So, well, that's not always the case. In MongoDB, it's the case that you use JSON to represent a document. But in general, they do use JSON objects to represent entities. And then, as I said, you're naming all your attributes. You can use lists for multi-valued attributes, so all the multi-valued attributes are stored together, so you don't need a join in order to get the multi-valued attributes. You also don't need a join to get information about your weak entities. They're physically stored with you, making your queries much faster. With composite attributes, they're stored as a single object. So they're stored together, makes it easier to think about them as a single object. Okay, so that's how they address storage, and the way they address performance is they're trying to eliminate, so 2 and 4 allow us to eliminate many joins. Okay, so 2 and 4 allow us to eliminate joins. So let's see. So sparseness, they address, so how NoSQL addresses things. NoSQL addresses sparseness with named attribute, named key value pairs. They address performance in 2 ways. One way is eliminate many joins. By storing multi-valued attributes. And weak entities with the parent object. They also get it by using a concept called horizontal sharding. Okay, and that is they distribute parts of the database across multiple servers. Okay, so in this case, horizontal sharding stores slices of the database on different servers. Okay, they also replicate. So the other thing is replication. They replicate. data across servers or replicate portions of the DB. Okay, so horizontal sharding, they actually use, I'm not going to get into it, but they actually use a hash function to hash documents to different servers. And then if the server goes down, they're able to, they only have to effectively rehash the documents on the server that went down. So they kind of use what's called a ring structure. So they basically will say, okay, let's say we have 3 servers. So 3 servers. What they're going to do is start hashing documents, document 1, document 2, say document 3 goes here, say document 4 goes here, document 5 goes here, document 6 goes here. Each of these segments is a server. Server 1, server 2, server 3. So they're using what's called a consistent hash function to map objects onto this ring. I mean, that's kind of, you could think of it as starting at 0 and going to 100. Another way you can think of it is just a continuum from 0 to 100, but it wraps around. So if it makes it easier, it really is just generating numbers in a range, but you think of them as wrapping around. And each server handles a certain number of the buckets. So if a server goes down, let's say server 2 goes down, then you could reallocate all of its things. You could say, okay, now server 1 goes from here all the way to here, and server 3 goes from here to here. Now that's not very good because server 1 got all of server 2's tuples. So they actually, see if I can, instead of, whoops, I don't certainly want that. I want a solid line. Let's go to here. So what, don't want a dotted line. Okay, I know I don't draw very well, but hey, this isn't art. I'm not in the art. So that's good because I used to do very badly in art class. Okay, so what they do is they actually create so-called replicates. So in server 1 would actually have server 10, server 11, server 12, maybe up to server 19. Server 20 would actually be, 2 would be 21, 22, up through 29. So there's in effect 10 replicas of every server. And they actually map these servers all over the place. So and they're not contiguous. Server 11 might be here, server 12 here, server 13 there, server 14 here, server 15 here, server 21 here, server 22. So each of them is getting a small part of the ring. So they're handling any tuples that go to that portion of the ring. Now there's actually only 3 servers, 1, 2, and 3. So everything that maps to anything that server that starts with a 1 goes to server 1. Everything that maps to something that goes to server 2 goes to, that goes to a 20 goes to server 2. Anything that maps into the 30s goes to server 3. Now if the server goes, let's say server 2 goes down again, so now 22, its things would be inherited by server 11 because those are the things closest to server 22. server 21, it would also go to server 1 because those are the things closest to, S14 is the closest to server 21. But maybe we have server 23, and right here we have server 31. So everything associated with server 23 would end up going to server 3. Okay? So what it means is that if you have n keys and k servers, if one server goes down, you only have to move n divided by k keys. Okay? All the other keys stay where they already were because they already stay. The hash function doesn't change. So all the tuples stay in the same place on the ring. It's just that all the replicas of S2 disappear from the ring and go to their nearest neighbor. So you only have to remap n divided by k servers. Those n divided by k keys now are put on or moved to the other servers. Okay? So this is how they distribute a database across multiple servers. It's called sharding. Okay? And because you have different servers handling different tuples, then operations go to different servers. Therefore, you don't have a centralized server like you do in a relational database that has to handle all the operations. Instead, you figure out which server is handling a certain document. The document is hashed to some server. You go to that server and perform the operations on it. So by this way, means through horizontal sharding, you're able to parallelize everything. Questions about that? Okay. So horizontal sharding and replication, actually, horizontal sharding leads to parallelization. Okay, C leads to less latency because you're able to get perhaps to a server that's closer to you or one that's less congested. Okay, now, what did I say was the problem with parallelization? Locking. Locking is an issue. Okay, so, and then the other issue, if you replicate, if you update one replicate, all the other replicates have to be updated as well, and the replicates that haven't been updated may be serving outdated information. Okay? So, what do we do about that? Okay, what NoSQL does is it uses a notion of eventual consistency. Okay? And for that, well, nope, we'll go here. Okay. So, this notion of eventual consistency, what does it mean? Okay. It says if there are multiple updates, if there are multiple conflicting updates, to different replicates, eventually the DB will converge, or all replicants, eventually all replicants will converge to the same value. to one of these values. So eventually it will converge to one value. So eventually you get consistency. What does this mean? We just punted isolation, okay? This punts isolation, or this breaks or violates the isolation property. Of acid. So eventual consistency actually doesn't violate consistency. It violates the isolation property. Because you could lose, if you have n conflicting updates, only one of them will be accepted. The other n-1s will be lost. Can a bank rely on eventual consistency? No. There is no way that a bank is going to be happy about, oh, we got 10 withdrawals and 50 deposits. One of those 60 will eventually apply to the database. And the other 59, yeah, we'll let them go. Okay? We'll be bankrupt in no time. Lawsuits galore. The lawyers will make a lot of money. So you can't use eventual consistency for things like banking transactions or inventory management. But you're actually kind of okay with it with social media. Okay? It's and again, I'm not in the social media realm, so actually was not able to find out exactly what things they're willing to sacrifice. I mean, if two people both post comments, you would think both of them would want their comment posted. So I'm not exactly sure how they do it or what they're sacrificing. I have to admit, I'm not in that research area. If any of you know, happy to hear about it. But I do know that that's what they're willing to give up. They're willing to have certain updates not make it into the database. But eventually, it will converge to one. We won't worry about how. It involves a quorum. So essentially, servers get to, quote, vote on which update they're accepting. I don't know how they do it. I just know they do. Once a quorum is reached, then all the other servers knuckle under and accept the outcome of the quorum. Okay? Think about the Iowa caucuses a few weeks ago. I know that was an utter disaster, but if you remember the first alignment, for those of you who followed it, if initially in the Iowa caucuses, you went to the group that supported your candidate. But if your candidate didn't get 15% of the initial people, then your candidate was discarded and you had to go to another group. And this continued until all groups represented more than 15% of the vote. Okay? Kind of like that, I suspect, for eventual consistency. Eventually, someone achieves a majority and that update wins, is my guess. Okay? Again, I'm not in the area, so I can't know that for sure. Okay, so we have semi-structured data for NoSQL. We have horizontal clusters. We have grouping of multi-valued attributes and weak entities to avoid joins. And the other thing that we do with NoSQL is we basically punt the query language for the most part, and we'll do, if we need to do things like joins, because they're still necessary, we will chase pointers. Okay, so we still can have foreign keys, but they really now have to be chased in the code that you write. So you're kind of back to that file system structure I talked about that predated relational databases. You have programmers that are now effectively writing the queries, and they may do several queries and then combine the result rather than having a centralized query optimizer break down the query into several subqueries and do it for you. So with a relational database, the database query optimizer figures out how to do the query, breaks it into subqueries, performs joins and everything, returns the result. You don't worry about how the subqueries are formed. In NoSQL, the final thing that improves performance, I guess I should have said this was 4. The final thing that improves performance is the programmer often writes multiple queries. Programmer writes multiple queries to execute a query, a complex query, rather than a database DB query optimizer doing it. Okay, so the programmer thinks offline. The DB thinks, the query optimizer thinks online. Right? It has to figure out in real time how to do it. So the programmer is faster in real time because the programmer did all their thinking offline. So it doesn't cost any computer time. Whereas the DB query optimizer has to do its thinking at runtime. That slows down performance. Okay? So, what do I think about? Actually, let's see. Okay, so are we good there? Okay. So, if you're an advocate of relational databases, this is your response. Okay, and actually just going to show it in my notes rather than writing everything out. Okay, your first response is, well, our query languages are much richer than yours. With your thing, you've gone back to the 1970s where if an end user wants a query performed, they probably can't do it. They'll probably have to ask a programmer to write it for them. This may take an unacceptable amount of time. So essentially, relational database people say you just sent query languages back to the Stone Age. Okay? If you look at MongoDB's query language, I liken it to assembly language because literally MongoDB's query language could be implemented using assembly language instructions. Okay, that's how primitive MongoDB's query language is. Oh, and by the way, MongoDB actually provides a query language. Many NoSQL databases don't even bother. Okay, so at any rate, a relational database person says, NoSQL sends query languages back to the Stone Age. Okay? Eventual consistency, not only is it difficult to implement, so it's not as trivial as I just made it sound with the quorum. It takes some doing. It's also not feasible a lot of the time in things like financial transactions or inventory management. Okay? If you're not, so relational database advocates will go further. They say, if you're not cheap, if you're willing to spring for the good stuff, which is storage area networks, then they actually do scale up very well to large loads. So storage area networks use shared memory rather than distributed memory. Now locking is pretty fast in shared memory. So over storage area networks, locking is pretty fast. You don't pay the same price that you do with the cheap commodity clusters used by NoSQL. So essentially, relational database management system advocates say, if you're running NoSQL, it's because you're running on a shoestring budget. And you don't have the bucks to afford the good hardware that would actually allow the relational database to run at an acceptable speed. Okay? The fourth argument relational databases make is, we're older and more mature, and NoSQL is young and immature. Well, NoSQL is actually getting a lot more mature, but the point is it's more stable. Okay? NoSQL is still trying out a lot of different things, so you don't have the same standardization that you have with relational database management systems. So people with relational database management systems will say we're more stable and we have standards. So there's a lot of continuity, which may not be the case with NoSQL. Okay, and then it turns out that relational databases, they're not that bad at handling semi-structured data. They just put it in another table. And if it so happens that your data is dense and not sparse, then it actually probably is a good idea to put it in a different table rather than using attribute value or key value pairs to represent the data. So it turns out that often semi-structured data really isn't sparse, in which case NoSQL storage blows up because they're storing attribute names. Okay, and the final thing is, hey, sharding's a good idea. We adopted it. We just co-opted NoSQL. We think horizontal sharding is a great idea too. And so MySQL, for example, uses horizontal sharding. So if you can't beat them, join them. Okay? So relational databases, in many cases, actually adopted this notion of horizontal sharding. Okay? Good with that? Okay, we're going to finish today with a couple theorems that have to do with transactions, and they're called the CAP and the PAC ELC theorems. Okay, so I'll go back instead of making you read all of this. So CAP is essentially the no free lunch. Okay, so in it says that you can have, there's three properties in a thing. You have consistency. Let's see, got to get this right. You have availability. And you have partitions. Okay, and consistency here means that redundant data has the same value. So replicated data has the same values. Availability means that a query will succeed and won't hang and not hang. Partitioning means that you can exchange, that there's not breaks in the network, that is contiguous, not partitioned. So everyone can communicate, not broken into blocks. So all servers can communicate with one another. CAP says you can have 2 of these 3. But not both. But not all 3. Say, no free lunch. You can't have all 3. Normally, the network is not partitioned for relational database management systems. Okay? So normally they get partitioned, so they just have to trade off between consistency and availability. What do you think relational databases opt for? Consistency or availability? Pardon? Consistency. They make sure, remember, that's ACID essentially, that you have to go from one consistent state to another. Okay, NoSQL opts for availability. And they use eventual consistency to get to consistency. But in the moment, they don't guarantee consistency. The reads you get from the LA server may be different than the reads you get from the Boston server. Okay? Now, if you do have a network partition, you can get both consistency and availability. Why is that? Because in the worst case, you're down to a single machine, which means it's easy to enforce consistency while still having availability. So if your network gets partitioned, you can get both consistency and availability, but that's bad. You don't want your network partitioned. Okay, so that's CAP. Then we have the other theorem. It's called PAC-ELC, which says, well, most of the time it's not partitioned. So PAC-ELC stands for if partitioned, do you enforce availability or consistency? Else, it's not partitioned. Do you enforce latency or consistency? So PAC-ELC is kind of a modification or extension of the CAP theorem. It says most of the time your system is not partitioned, so you'll be in the else situation. If it is partitioned, then you choose between availability or, and just make sure. Yes, so in case you, I just messed this up. This is what happens the first time you do something. Okay, just a second. Let me make sure I get this right. Okay, I'm pretty sure I messed up partition. So with partitioning, so normally you are able to partition the network. Okay, so I messed it up. Normally you are able to partition because you have message passing going back and forth. So most of the times you are able to partition stuff, and then the question is, do you enforce availability or consistency? So this is CAP. But if you are partitioned, that is, if stuff is getting dropped, okay, do you enforce latency, meaning you still want fast response to queries, or do you enforce consistency? So if messages are starting to be dropped, meaning partitioning is now failing, relational databases opt for consistency. So they will stop responding to your queries until they can ensure that everything is consistent. Whereas most NoSQL systems will instead choose to enforce latency. They will continue to provide results knowing that they will eventually converge to consistency. So relational databases will enforce consistency. Many NoSQL systems will opt for latency. So generally, you will say that relational databases are what are called PCEC, meaning that if partitioning is working, they enforce consistency, else they enforce consistency. Whereas many NoSQL systems, if partitioning is working, they provide availability, else if partitioning is not working, then they provide or reduce latency. So with the PAC-ELC theorem, you have two sets of choices. One if partitioning is working, else if partitioning is not working. Okay? So basically, NoSQL is about speed. Relational database management systems are about consistency. If you're willing to tolerate losing some lossiness in your updates, NoSQL may be right because it can increase performance. If you cannot tolerate lossiness in your transactions or conflicting transactions, you need to go with a relational database management system. Okay, so that's essentially the trade-off. Lossiness, okay. NoSQL, okay. Lossiness, not okay. You have to use a relational database management system. Okay, today's Thursday. On Tuesday, we will talk about MongoDB, which is probably the most commonly used NoSQL database management system. And a lot of it is just going to be me having you work queries rather than me lecturing at you. Okay, in fact, I'm probably will have a brief introduction to MongoDB, and then I'll probably have you start working on homework 6 while I'm here so I can help you. Okay, so I'll see you all on Tuesday. I will have the review materials up shortly.